All right, I'm going to present our speakers here. And so we have Dr. Wang from the University of Montana, the chemistry department, and an alum, Collin here as well, who worked with Dr. Browder, and they're going to essentially try to recruit students to come to University of Montana, which I was there last fall, and it is a beautiful campus, I have to say. So with that though, I'm going to turn it over to are you guys gonna both come up here and present? Okay.
So, well, thanks, Naomi, and for the invitation. And it's been a great day visiting here, talking to many of you. Had lunch with some of you. It's great. And um, we are here trying to broadcast ourselves, and trying to attract some of you to consider University of Montana as a great place to study, chemistry, as a graduate student. So, this is not a usual like a research talk I typically do. I'll try my best. So, here, this is Missoula, basically. By the way, all the pictures that I show here today are taken by either Collin and myself. So you'll see what they look like. So basically, University of Montana sits in a college town called Missoula in West Montana. I'll show where that is in the next slide. So, it's a typical summer afternoon where you can hike all the way to the mountain, to the top of the mountain, and take a few shots like this. So the Lewis Clark River runs through the town, which is nice. And the campus, this is the campus that sits right on the foot of the mountain jumbo. And you probably notice an oval like landmark. That's where the center of the university is, and the football stadium. The chemistry building is actually on the south part of the campus. So whenever I go out to give talks, normally the first question I get is, "Where's Montana?" or "Where's the University of Montana?" Right? So I figure out it's better to show that on the map. So here, this is where we are right now, and that's where we come from, right? So University of Montana Missoula is on the very west in the state of Montana, and that's here, right? Some people like to confuse us with another institute here at Bozeman. That's called Montana State University. We're not the same, right? We're friends most of the time, but not always. So the UM folks, we call ourselves Grizzly because that's what our mascot is. And the Bozeman folks, they call them Bobcats. So yeah, we're both meat-eating animals. We fight. Yeah, but we also get along. And yeah, that's not that's most of our relationship looks like. But yeah, here it is. We are very north, up to the country. It only takes 3 hours if you want to drive all the way to the Canada, yeah, across the border. So Missoula is right in the middle of Glacier National Park and Yellowstone National Park. So it's beautiful. Got a lot of tourists in the summer, and a lot of nice view and scenery. It's pretty hard to keep students in the lab in the summer. So I try to have group meetings, when we hike, we take the whole group, I take the whole group for hiking and try to talk about the science along the way. So that's doable, right? So, more pictures. Well, a little bit of overview about the university. So, Missoula is a town with, rough population 80,000, similar size to here. And the UM, has about 11,000 students, smaller than here. About 8,000 undergrad and 3,000 graduate students. Small university means most of the programs are small. So Missoula has a climate that's very similar to here, with a lower elevation, almost half of here. But because we're further north, so that the temperature and climates are quite similar. And we see a lot of deers, as we see a lot of squirrels. So deers are okay. The feeling is kind of like the first day when you travel to Yellowstone National Park, the first day you see a buffalo, you see, oh, that's buffalo. Beautiful, nice, wonderful. And you spend a couple of days there, and last day you see buffalo. Oh yeah, it's buffalo again. Standing in front of the road, blocking the road. So yes, that's how we feel about deers. Deers are everywhere. There's a during the hunting season, you can hunt the deers. But if you live within the city limit, well, there's nothing you can do. They eat everything. They destroy your garden. That's not very pleasant. This is the main hall where the president and the upper administration work in this building. And behind this building, you see this mountain and this M character that that of course M stands for Montana. And there you probably see the zigzag shape trail here. That's the hiking trail that could lead you all the way to the mountain to the M character. This is a very fantastic exercise, recreation place. I see a lot of faculties and employees, after lunch, try to hike a little bit when the weather allows them to do that. I do that myself. So when you do that, go up to the mountain. If you like photography, you get a nice shot, something like this. This is what I took last year. It is early of the fall. You start to see the leaves, of the maple trees become red. And this is the chemistry building. Actually, the leaves of the ivies turn red. Quite nice. And even if Missoula is way north, we still have 4 seasons, right? Spring, summer, autumn, fall, and winter. Although the winter can be long, but if you are sensitive enough, you can get a nice photo pictures, something like that. Spring, summer, fall, and winter. Yeah, and then those are those are my work. Well, that's one of my hobbies. Something I like to do. And Missoula has also a very rich like outdoor and animals and plants and way more than you can take like take a shot, something like that. Again, if you like photography, well, here, although I'm here mostly to talk about chemistry, but there are other things that you do want to explore and go out and explore. So Yes, now let's talk about chemistry. So the chemistry department at the University of Montana, first small. We have a small PhD program. We have a small department. You know, by counting, we have about 19 faculties, and with you know, a small PhD program, about 30 graduate students. So if you calculate the faculty to student ratio, yeah, that feels pretty good. And you know, it's a R1 research institute, which means that we have a you know, um, I would say, you know, satisfactory research funding that support the faculty research. We have, you know, very state-of-art instrumentations, including new, you know, X-ray diffractometer and, you know, very fancy NMR spectrometer that allow us to pursue the chemistry agenda that we want to pursue. And although the program is small, but we have faculties work on almost every you know, individual area of chemistry, you know, synthetic, analytic, biochemistry, and even chemical education. We have faculty there working on these areas. And our graduates go to both academia and industry for career. And those are some of the representative places they land on. So, you know, we support our students both in research while they are in program, and we also support them, you know, after they get out of program for, you know, further career enrichment and development. So some specific, you know, like introduction to our faculties. These are the, you know, leadership groups. We have you know, Professor Bruce Bonner, you know, just stepping as the interim dean for the Leo College of Science that, you know, is newly founded during the summer. Previously, the science departments are within together with humanity and social sciences, and then we try to divorce them, and and yeah, now we have our own college, and we have our dean from our own department. Well, you know, yeah, and it's proud to say that here. And you know, Professor Ken Southern is currently our chair, very nice guy. And you know, Professor Eric Thomas, who Naomi knows a lot about and collaborated a lot with. He leads the Native American Research Lab, and it's quite successful in terms of you know, recruiting students and securing federal grants. And Professor Mark Krakalici, that's our previous chair, who is working on the chemical education. It's, you know, we are one of the very few programs that still have the, you know, innovative faculty work on this, you know, this area doing research. And department-wise, we have people working in the analytical environmental chemistry area, doing, you know, all kinds of environmental science, study aquatic chemistry or atmosphere chemistry, separations, chromatography. We'll highlight some of them individually in a later slide. We have a synthetic group of synthetic people who work on, you know, inorganic synthesis, inorganic chemistry, organic chemistry, even solid state material chemistry, doing crystal engineering. We'll talk these folks a little bit more in a bit. And lastly, we also have a group of you know, biochemists and or medicinal chemists who work on, you know, protein structure dynamics and or, you know, vaccine, you know, a natural product or computational chemistry that help those people to understand, you know, how biological components interact with each other. So many of our faculties are research active. They play important roles in our department and both in in the university wise, promoting the scientific research and really support, our university in, to maintain its R1 status. Among these, there are a few, of my colleagues that I want to give the few words about. This is Professor Ryan Berryman, who is an expert in organic chemistry, specifically in supramolecular assembly and long covalent interactions. His research focused a lot of about doing study how halogen and hydrogen bonding interacting and interface with catalysis, ion transportation, and self-assembly. There is a lot of interesting chemistry or work going on at the interface of organic synthesis and the biology, especially. I'm quite interested in the so-called artificial ion channel that he and his collaborators are trying to develop. And speaking of environmental or analytical chemistry, this is actually our rising star, Professor Lu Hu, who leads atmosphere chemistry lab. Study smoke, the effect of a wildfire smoke to our environment. So what he utilized actually is quite interesting. It's a mix. Well, he used a lot of tools, right? He has a satellite surface observations, and even they have a aircraft. Well, I'm not saying he has an aircraft, but the way how these the people in the atmosphere chemistry work is that every summer they put together a campaign type of research activity, and everyone put their instrument on a NSF aircraft. They fly through the smoke areas. Well, this is quite a bit fun. And they try to detect different things and try to monitor where the smoke go and what kind of materials the smoke carry and how would that affect the the ecosystem. They do a lot of burning, either wildfire or controlled burning. In a season, if the wildfire is not done, is not done too much, they'll set a fire themselves. Which get a lot of jokes. From me, and and we have specifically we have two young research assistant professors really into some of the new disciplinary areas of chemistry. For example, Asha Rio, she is a graduate from our department and decided to stay as first as a postdoc and later start to develop her own research program. His work is focuses on the design and synthesis of small molecules that can interact with the big molecules or the biological molecules for therapeutic and diagnosis purposes. And she really takes advantage of the organic training and instrumental training that she got while being a graduate student in our department, and start to work with her students upon becoming an independent PI on this very interesting subject. And so is her husband, Dr. Dan Decato, who again was a graduate student in our department, and later decided to first take the positions as the facility managers to manage the small molecule X-ray core facility as well as our NMR facilities, and later become interested in crystal engineering and chemical, trying to really study the click chemistry that could happen within the crystal solid state, within the crystal lattice, like some of the work he has demonstrated, showing that as long, well, actually the click chemistry can actually happen within crystal without any solvent, as long as you have the molecule stacked in the right alignment. Which is pretty cool. What do you need? The only thing you need to do is to, well, get the precursor, crystallize them, give a little heat, right? And that would make the that will click together and make the product. This is quite neat. That save a lot of effort, like purification and isolation and other stuff. So, quite interesting as well. But we're here mostly to talk about our research. So, from this slide, you will see what we do there at in Missoula. So we are a bioinorganic chemistry and bio-inspired catalysis lab, which means we focus on the metal, right, in biology, and mostly we study what they are, what they look like, what they can do. So more specifically, we like to study a bunch of high valent so-called oxo intermediate or long oxo intermediate, and trying to teach them, right, to do interesting organic transformations that are important. For example, converting inert hydrocarbon to functionalize the product, as well as for example, splitting water to make O bond and generate O2, and and power energy sources. So in my lab, the student get exposed to pretty much a little bit of everything. We do synthesis a lot, both organic and inorganic synthesis. We do kinetic measurements, study how our oxidant react with substrate, and in which kinetic model. We do a lot of spectroscopy, right? We use those tools to characterize interesting high valent species, reactive enough to oxidize our substrate. We want to understand better, what they look like structure-wise, what their electronic properties are, and we, some of the spectroscopies we do on site in our department. Some of the very specialized spectroscopy we collaborate with other people across the country. So we do a lot of collaborative research. So there is an electron chemistry component in our research where we study electron transfer, and maybe coupled with other chemical reactions like proton transfer or bond formation, bond breaking, events. And we do a little bit of computation in this part. We mostly collaborate with other people who utilize their expertise to help us understand the molecules that we make. So yeah, a taste of everything that really have our student gain a set of comprehensive experience. When they get out of the group, and they are, I make sure they are well equipped to explore other things and to be able to use their expertise in their next stop. So a little bit background about the research that we do. We focus a lot on the so-called CH bond functionalization. On the molecular scale, it means you cleave a carbon hydrogen bond and put back some other functional group onto the carbon center to form a carbon X bond, where the X could be oxygen, could be nitrogen, could be halides, could be some other atoms. Right? This way, and this fundamental transformation sees a lot of application in many fields: organic synthesis, petroleum industry, pharmaceutical industry, agricultures, and materials. Right? So it's an important fundamental reaction, but has a big picture of applications. How do we do that? We take lessons from nature, and nature has taught us the best way of doing that. For example, I show here two representative example of metallo enzyme that could functionalize carbon hydrogen bond of those molecules. The first one is called soluble methane malloxgenase, with a synchro acronym SMMO. It's a multi-component enzyme that with the biggest component being a hydroxylase. The chemical reaction that this enzyme catalyzes is to convert methane. Right? If you based on the organic chemistry, we know that methane has a very strong carbon hydrogen bond, 105 kcal per mole, very hard to break. And however, this enzyme knows how to do that, not only under mild conditions, but very selectively. Right? It breaks only one of the 4 bonds, insert one of the oxygen from O2 to make methanol. Right? And if you compare the bond strength in methane and in methanol, the methanol actually has a much weaker CH bond. So the question always, people always ask is that, why is this reaction keep going? Right? Since now the product is much easier to be oxidized than the substrate, right? And of course, that's the beauty of this enzyme. The enzyme knows how to stop here, right? Without over oxidizing the substrate. So if you take a closer look at their active site, it looks like this. It has 2 iron centers. All right, and the mechanism has been well studied for this enzyme, over the years. My PhD advisor, Professor Larry Kay from Minnesota, contributed a lot to this understanding, particularly in a mechanism like this. So with the help of this reductase, the resting state, the iron 3 gets reduced to iron 2, both of them, which is readily available to activate O2, first forming the peroxyl type intermediate, and then continue to cleave the O bond, forming this so-called di-iron 4 bis-mu oxyl diamond core intermediate. Yeah, and this intermediate is named after K, so people gave the name intermediate Q. Right? So this is the most interesting intermediate to us, because iron 4 plus 4 oxidation state, you don't typically see that. Right? For iron, it's typically plus 2 or plus 3, right? But it's only when the enzymatic catalytic cycle reach this hot level, right? And this intermediate is then responsible for cleaving the CH bond on methane and put back 1 oxygen, and complete the cycle. Now, this is what an enzyme can do. As a synthetic chemist, we ask ourselves if we can develop a artificial system with a similar type of core structure that can do this a similar reaction. We're still working on that, not quite yet. Mostly because methane, the CH bond is too strong. So far we can get to like lighting close to 100 kcal per mole, but still a few kcal per mole away from methane. Another example is a mononuclear enzyme called tau-D, taurine dioxygenase. And this is the chemical reaction that this enzyme catalyze. It specifically attack this carbon center, cleave the CH bond, install back the hydroxyl group, so to make it alcohol. And this is the crystal structure of this enzyme. It's a mononuclear. Means that there is only one iron center in there. And the catalytic cycle has been studied mostly by Marty Bollinger and Carson Crabb at Penn State University. And following a similar pattern or the mechanism, the iron 2 activate O2 first to give rise this so-called high-valent iron oxide intermediate. If you recall what I have here in the previous slide, this is a dimerized form of that, right? But you see oxygen, you see higher in the +4 oxidation state. So this hot intermediate now is responsible for cleaving the CH bond of substrate and put back the hydroxyl group to the carbon to form the carbon oxygen bond and release the alcohol product and complete the catalytic cycle. So now, if you take a look at the periodic table and you pay attention to the literature, you notice something really interesting. So nature utilizes iron a lot as a native metal, right? Like in the two representative examples I showed you, they are both iron-dependent enzymes. Nature also utilizes copper a lot, right? There are a lot of copper-dependent enzymes, but for some reason it skips the two metals in between. Cobalt and nickel are not quite used by nature yet. There got to be a reason why. Some of you might argue, well, iron is the most abundant element, right? Metal element on the Earth's crust. Yeah, which is true, right? So, for example, this figure tells you the relative abundance for a bunch of metals on our Earth's crust. You see the iron standing out really. But if you compare the abundance for some other metals like copper, nickel, and cobalt, they are not very different. So abundance is one reason, but that cannot be the only reason. So when I first when I start my group and think about what to do, then I thought maybe this is something that I can step in and make some contributions using synthetic approaches and trying to mimic the enzymatic active site structure and properties, but swap the metal from iron or copper to cobalt and nickel. So I give you a brief overview about the research project that are active in my group. So first is the dinuclear project. Yeah, this looks familiar, huh? So we were able to make a dicobalt bismuth oxide for membrane diamond core structure, and found that oxidize one of the cobalt. We're not there yet to oxidize both from cobalt 3 to cobalt 4. So yes, we can access the high valent +4 oxidation state for cobalt, and this happened to be a very reactive oxidant. Do a better job than iron and copper and manganese. We don't know why. Still working on that. And from there are many directions we can go and many fundamental bond cleaving and bond formation reactivities we can explore. For example, CH bond activation, or CX bond formation, OO bond formation, or even carbon nitrogen bond activation and functionalization. And we published some of our results on you see in some of the very top journals, and we're trying to produce them. Another project that are active in my lab is a mononuclear project, where we're able to get to synthesize and characterize. We even get a crystal structure for a mononuclear cobalt 4 species that binds with two nitrate ligands. Right? And then, starting from this initial publication, we can, explore other, directions. And Collin will be telling you a little bit about his project, which is on the nickel analog. Again, there are many interesting directions, and we want to explore, and we're eagerly seeking talented student to join us. So this is my current lab. So 30 graduate students, you see Collin, maybe very different from what you remember. And this is Michael, this is Wenting. And as I said, we collaborate with many other groups across the country. Some, here just list a few of them. And we are well-funded groups. We got a constant funding from NSF and the NIH, and with active grants and with some pending grants. So we have the idea, we have the money, we need more hands. So I think Collin will take over from here and give you some specifics about his experience from a graduate student perspective.
All right. Yes, it's good to see you guys. It's good to be back at NAU. My name's Collin Bryant. I'm a second-year graduate student in Dr. Wang's lab, studying some bioinorganic coordination chemistry. So I stuck this picture up here. It might be more recognizable for myself. Yeah, I cut off my hair. Wanted to get more serious. So I thought it would be appropriate, fitting to describe my path and what led me to University of Montana. I started out at community college, which I knocked out my general education credits, got my associates, my first 2 years of bachelor's. And then I transferred to NAU and finished up my chemistry degree. I graduated 2024. I guess that's a year and a half ago, almost 2 years ago, and I got my bachelor's in chemistry. And as I was thinking of grad school, I came up with 3 priorities. I wanted to have a school. Of course, number 1 priority was a good research program offering PhDs. So I wanted a decent place where I could get a PhD. I also, after, finishing up my bachelor's, I had to play catch up. Well, while I was at NAU, I had to play catch up because I couldn't complete all my chemistry credits. So I had to squeeze 3 years of a chemistry degree, which is, as you guys may know, is pretty intense, into 2 years at NAU. So I was very stressed, but I knew I wanted to go to grad school. So I knew the place I would go would need to offer me a good balance. So I wanted a place where I could have some semblance of a work-life balance. So you might think quality of life in grad school, those are oxymorons. That's a juxtaposition, but I went for it anyways. And then I also wanted affordable living. So I kind of looked at some places. I knew I wanted to get out of Arizona, get out of the heat. I looked at California, good schools, maybe not the best quality of life, and affordable living was not good. So I moved to Oregon. Maybe good research, quality of life, affordable living, maybe. I wasn't totally sold on Oregon. Washington, kind of the same deal. And then I moved in and I found Montana. I'm a big outdoors guy. I love to snowboard, fish, hike, backpack. So what better place than Montana? So yeah, that's how I ended up there. So you might be wondering, as prospective graduate students or people who are about to graduate with their bachelor's, what is grad school really like? I mean, that's kind of the big question. Like, will you really like grad school? Is it a good fit? So I hope to elaborate on at least what it was like for me. So first year experience, there's a few milestones you have to, or a few things you have to knock out. So proficiency exams, as soon as you get there, you have to prove your proficiency in at least 3 of the 5 ACS categories. So physical, inorganic, analytical, organic, as long as you pass above 50%. And I think those exams, the ACS exams in particular, they're meant to be hard. I think they're meant for the average to be like a 50. So they are hard exams. So once you get through those, even if you don't pass them all, you can take remediation courses where you can improve or prove your proficiency in one of those topics. So then I would say the vast majority, very few incoming graduate students don't do TA. They don't teach labs. So you'll get a TA assignment. I had experience TAing for Gen Chem upstairs here at NAU, so I got assigned to Gen Chem. But we have Gen Chem, Intro to Gen Chem, Organic, Intro to Organic. You'll be likely assigned a TA assignment. And then you might want to consider, at least in your first year or first semester, some lab rotations or a lab selection. And then you'll want to put together a committee once you decide what your topic or what your research field is going to be. And then I think the one thing that's not said enough is adjusting to graduate pace. So undergraduate is very fast paced, and you're doing a lot of things in such a short period of time. Graduate school is kind of like the opposite. Well, you're still doing a lot, but the pace slows down and you're doing bigger things, and just adjusting to that and not spinning so much, that can be difficult. As far as coursework goes, you need to take 6 courses, so I think it works out to like 18 credits. That translates to about 4 semesters. So within the first 2 years, you'll be done with the courses, and then after that, you'll be on to research. Small class sizes I've noticed at UM again is a small college, about a third of the size of NAU. And I've had courses maybe with 8 people or 10 people. I think I had one last semester with 3 people. So very small courses, good interaction with professors. I found it very easy to learn in those courses. And again, you're there to improve or prove your proficiency. So when I graduated from NAU, due to my courseload, I didn't really click with organic chemistry. So I took a remediating organic chemistry course, and now I know how to push arrows and push electrons. And I'm good at mechanisms now. So that's a good thing. So don't feel bad if you don't get the proficiencies. I'd say the biggest thing, aside from proving your proficiency, is interacting with professors and other grad students. So these professors will most likely, just numbers, odds are they're going to be on your committee. It's good to interact with them and also interact with other grad students. Make friends, become familiar with your cohort. As far as TA duties, if you haven't TA'd, typically, from my experience, it's 2 3-hour labs per week. And each lab is, I don't know, I put about 20, but some labs may have less, some labs may have more. I think it's capped at 24, but you typically have 40 students total. You may be expected to prep lectures or pre-lectures and weekly grading. I love teaching. It's so fun interacting with students and setting them free to play with chemicals, but grading is not so fun. It's a time sink, especially when you have research to do, but it's part of the job. That's what you get paid to do when you're on TA. And then for your midterms and finals in the lab, you'll have to proctor those exams. RA duties, if you advance from TA to RA, then you'll be expected, this is where you're a research assistant and you're actually researching and gathering data. So you're going to be expected to read the literature, get familiar with your field and the area surrounding it, conduct lab work, of course, analyze data, and perform lab maintenance, come up with lists of materials that you need to get your work done. Yeah, I think this is fun. Work-life balance, it is possible. It may not be as much as you may like, but especially in Missoula, when the activities are just right in front of you, you can go hiking right off campus or ride your bike around town. I'd say just set sensible expectations, and by that you mean the key word is sensible. You'll have to sense what you're capable of. I say time management is a big part of it too. So find your routine, find what works for you. If you're a morning person, show up in the morning, get your work done. Me, I'm not personally the best morning person, so I like to spend my mornings myself, and I may show up 10, 11, but I stay till 6 or 7. So find what works for you. And don't forget, rest and recuperation are an honor. So rest, sleep, drink water, eat good. Those are, I think those are the 2 most important things, sleeping good and eating good. which those are often at odds with your graduate experience. But just try and do it. Take a day of the week and do your laundry, clean your house. Yeah, so in Missoula, there's unlimited outdoors. You're in western Montana in the mountains, like Dong said. You're 3 hours from Glacier, and I think 4 or 5 from Yellowstone, and there's endless places in between. I love to fish. I love to hike. There's countless rivers and streams to get nice catches on. And amenities. I mean, Missoula has a Costco. They have a mall. They have everything you need. Walmart, grocery stores all around. Everything you need is in Missoula. So I'd say overall, it's a good place to go to grad school. It's a place I feel like I can thrive. So now let's talk about some chemistry. I know a lot of people, they become interested in organic synthesis or synthetic chemistry. And that was me too. I was interested in like drug design, some synthetic chemistry, but I also was interested in inorganic chemistry as well. So this lab kind of fit me from that sense. So here's just a representative synthesis of a complex that I've been working with. So the first step, you have some imine condensation. Then you do some organometallic chemistry where you treat it with, it's an interesting reaction. Trimethyl aluminum coordinates to this and then initiates a methyl transfer. And you repeat that 2 times to get the methyl on both sides to reduce the imine to the amine. And I think these two steps are air sensitive. So there's a bit of Schlenkline or glove box techniques that you may acquire, and even some cryogenic conditions. So once you have the ligand, this is the pyridine bis amide ligand or amine ligand. Treat it with a strong base, which is a lithium organolithium base, and then a nickel chloride salt, and it has pyridine attached to it. So that's conducted in toluene at cold temperatures to room temp overnight. Essentially, I say 18 hours. Let it stir overnight, and eventually you get this air-sensitive nickel 2 complex with the pyridine coordinated to it. Treat it with silver fluoroborate, which is silver plus. It wants to be silver 0, so it'll steal an electron from the nickel center and oxidize the nickel 2 complex to the nickel 3 complex, and you have the non-coordinating or weakly coordinating fluoroborate anion to act as charge balance for the salt. That crashes out in toluene, and then you can extract it in DCM and treat it with the sodium salt, so nitrate, fluoride, acetate, azide, cyanide. The most stable one is hydroxide, so I typically isolate it as a hydroxide, and that is air stable and can be stored as a beautiful green powder. I wish I would have put a picture of it up, but here's a picture of it in solution. This is a very dilute solution too. These are transition metal coordination complexes, so they have large molar absorptivities, and they have very, very intense colors. I love the nickel 3 green color. It's very nice. This is a crystal structure. This is a structure obtained from a crystal grown of the nickel 3 complex. So you can see it. It's one thing to see it in the 2D plane, but this is it in 3D space. And then I went ahead and did some ligand exchanges, and it's interesting to see the color change when all you're changing is that X from nitrate to hydroxide, each of them. The color on the screen doesn't really pick it up, but this is like an olive green, and it slowly gets lighter or changes hue to more like a royal emerald green. So I think this is fun chemistry to me because it combines organic synthesis with some inorganic chemistry, and it hits on both those things that I really like. It's fun. So as far as the research progress, why do we use that complex? It's because it's a highly donating dianionic amide ligand, and it can stabilize these high valence states. And a previous lab member, well, he's still in the lab, but he did work on cobalt, the cobalt analog of this. So he used this, and then instead of nickel X, it's cobalt X. And he observed the trend where cobalt X, as you replace X, the coordinating anion, with a more basic anion other than nitrate. So fluoride, acetate, azide, cyanide, hydroxide, those are each increasing in basicity. You get a higher reactivity. So by reactivity, we're looking at HAT or HAT, hydrogen atom transfer. So CH bond cleavage, sp3 CH bond cleavage. So he found that the more basic the coordinating anion, the more thermodynamically and more kinetically potent of an oxidant the metal complex was. So I investigated that this summer with nickel 4, and what I found was, in general, it displays the same trend. So going from nitrate to acetate to hydroxide, which are all oxygen coordinating anions, both the thermodynamic reactivity, so it can cleave stronger CH bonds, and it also does it faster. The kinetic reactivity increases as well. It was interesting too. Well, fluoride is not much more basic than nitrate, so there was imperceptible change, so that was fair enough. But the azide and cyanide seem to be special cases where they did not follow the trend. So that is going to be worth more investigation. I'm not sure why, but I suspect it could be due to some pi acceptor capability with the azide and cyanide anions. Nitrate, acetate, and hydroxide are poor pi acceptors, so maybe there's something there. So we have the kinetics. Basically, we take a UV vis spectrum and monitor it every 0.5 seconds, and you have these different species. So the nickel 4 will have a characteristic band, and you track that on the UV vis. And you can observe how fast it reacts. So we know that it's reacting faster. So here's nitrate, acetate, and hydroxide. So the rate increases with the more basic coordinating anion. So it's reacting faster, but how do we know that it's actually cleaving the bond? Well, we analyzed the products. We did some product analysis with GCMS, and we found some oxygenated products. So, for example, toluene turned into I think it was acetophenone, or no, that was ethylbenzene turned into acetophenone, and we suspect that's because when this oxidizes a hydrocarbon, you produce a carbon-centered radical, and that is quenched by oxygen, which is in the reaction media. So that's how you result in oxygenated products. But that's not just the goal. We don't just want to cleave CH bonds. We want to find a way to teach the complexes to not only break the CH bond, but install something else on it. And it's funny because these high valent states, we can access those, but once it's oxidized to cobalt 3 or nickel 3, the complex is happy right there. It's not going to go down to nickel 2. So if we want to functionalize hydrocarbons, not only just activate the hydrocarbons, that's a 2-electron process. So we need to go from cobalt 4 to cobalt 2, or nickel 4 to nickel 2. And right now we're only getting 1 electron reactivity out of it. So we need to find a ligand that's less stabilizing for the high valent state, which is interesting to think about. So we need to destabilize the +3 state by installing electron withdrawing groups on the ligand. Essentially, these dianionic, or these amide in donors are giving too much electron donation to the metal center. So we need to install something on key positions of the ligand to withdraw some of that electron density from the metal center. And we have this calculated DFT, some quantum calculations for the d orbital splitting diagram, and it rationalizes our synthetic pursuit. If we install electron withdrawing groups, we will remove electron density from the DYZ anti-bonding orbital. And if you remove electron density from the anti-bonding orbital, you will stabilize that anti-bonding orbital. And since that gap increases, this is a better electron acceptor. So it can be more easily reduced to cobalt 2 or nickel 2. This strategy would be analogous for nickel. So we know we need to install electron withdrawing groups, and these are future directions, but we just don't know how exactly or what type of electron withdrawing groups. So we suspect maybe install some fluorine groups at the alpha position to the amide. Or, methyl groups are electron donating. What if we just eliminate the methyl groups? Or what if we install trifluoromethyl groups on the para positions of the phenyl rings? What if we only do some combination of the two? That's what I'm not sure about. we'll need to do some experimentation. We'll need to actually synthesize these ligands and characterize those complexes. So there's many different directions that this project can go. One of them has to have the key. So overall, this is a video. I think I was so proud of myself this summer because I cleaned the dirty schlenk line, but for the picture I forgot to clean my hood. But I was happy I overlooked this. You don't want to get too happy in the lab. That can lead to mistakes. Overall, we present a multidisciplinary approach to designing and characterizing novel systems for sp3-CH activation and functionalization, and more frontier areas, as he talks about with the dicobalt species. As Dong also said, we incorporate a lot of different areas in chemistry. So inorganic, organic, physical, organic, organometallic, biochemistry, analytical, theoretical, and computational to some extent. All those fields are used extensively in our lab. So if you have any interest in those, then you may be a good fit here. And I like the wide breadth in our study because it really gives me, a student, as a lot of room for growth because there's a lot of stuff to learn. I came in here because I like synthesis and inorganic chemistry, but there's so much else to it. And it's all on the frontiers of research. I mean, there's groups out there, but we're pushing it. This is frontier research. Impactful publications. There's a good track record in the Wang lab, and we're funded well. And as you saw before, many projects need many hands. So overall, kind of a summary. Work-life balance is good. I feel like, yeah, he was right. It is hard to be in the lab in the summer, but it is good. It's possible. And especially in a place like Montana. The facilities are good. You have a brand new NMR. You have walk-up NMRs that you could get on whenever you want. They're really accessible. GCMS, same thing, state-of-the-art. Single crystal XRD, so we can acquire our own crystal structures, which is really convenient. And I heard we're getting a new one, and that's going to be really neat. So we do have good facilities to conduct good research. Like I said, frontier research in bioinorganic field, the Wang lab track record, funding. So we have RA opportunities, and then he alluded to this, but if you look into Larry K and John Groves, he did it. His PhD at Twin Cities under Larry K. and John Grove did a postdoc at Princeton. These are, you could call them fathers of the field, but at the very least, they're seminal figures in the field of bioinorganic chemistry. So he's very well trained, and you have a lot of access to him. I never see any other professors active in the lab like him. He'll come in, help with experience. Yeah. So all in all, I think I really lucked out with where I ended up, and I enjoy life at UM. So here's our contact information. We have Dong's email, my email. To get it, it's just first name, last name at UMontana.
Hey, you missed one. No.
What? Oh, Dong Wang 1. Sorry, I forgot that.
Between the dot.
Dong
One.
1 dot. Sorry, that's a typo.
That's a weird, yeah.
Dong 1 Wang at UMontana, and then Collin Bryant at UMontana as well. If you want to get in contact with the grad school, you could email this one. And then our university, or our chemistry department website is umt.edu/chemistry/. And then if you are interested in applying, the application is due December 15th, that's the priority deadline. But if you submit it a little after, there's a chance it's as needed by spots. So if we have space, yeah. And here's a view from the other day at campus. So I want to thank you all for your attention, and we're really happy to be here today with you guys. And Dong and I will open. You can direct your questions to Dong, and he will forward them to me.
A question on the chat.
On the chat.
Yeah, you want me to read it?
Yeah, could you?
Yeah, this is from Alexis. Says, hi Colin, thanks for sharing about your research in time in Montana. I have a question about your research. Aside from our previous lab mate messing with the sea cobalt at species of a molecule you modified, why look at this particular molecule? Is it seen in nature often or used in a specific reaction?
These, okay, I believe Alexis, she would be talking about the ligand scaffold. So why do we want to characterize this ligand scaffold? Well, because we want to investigate the reactivity of the metal. So we want to hold the ligand constant and see how the metal performs. So if we change the metal and compare it to the cobalt species, then we could get data that tells us about how the reactivities of cobalt and nickel compare to each other.
And in future directions, we plan to expand the selection of metal to include other things like copper, iron, and manganese. I think this is a great platform that allows us to study and compare, the difference in reactivity that originated from the metal when keeping the ligand identical. So, to really help us understand the property of the metal.
And I would also add that this metal is, or this ligand scaffold is kind of our prototype. We've already established with the cobalt and starting to establish with the nickel work that it's an outstanding way to stabilize the high valence states. And now we're looking for ways to modify the ligand scaffold to tune the metal center. So we wanted to nail down the cobalt and nickel with this prototype scaffold and then move on to different modifications of the scaffold. And shown here. Thanks, Alexis. I think, yeah, Dr. Hurst.
So thank you for a very nice talk. That was really enjoyable. Two-sided question. One, you could consider thiocyanate, SCN, as an adjunct to compare against azide. It'll probably bind through the nitrogen, especially with nickel to ore, but that might allow you to probe what's going on. Second observation or question, REU program, a chance for people to get up there during the summer and discover how wonderful it is and want to come back. Does UN have an REU program?
We used to have an REU program, but that program was ended a couple of years ago. But if you have a student interested in some sort of summer research, let me know. We can plan.
I could probably find somebody.
Sounds like we could set that up. Yeah.
Well, depend on which group they are interested in doing.
This one, clearly.
Oh, thank you very much. Yeah, I can tell you, if we have funds to support students doing some research with us. It's not a problem.
Thank you.
Thank you. Dr. Lindbergh, Garrick.
I have a similar pair of questions. The first one is, if students reach out, is there an opportunity to get application waivers?
Fee waivers. Yes.
Yeah.
That seems to be a big difference in a lot of students' plans.
That, okay,
Yeah.
absolutely.
Make sure I
Yeah,
let
we should have
students
mentioned
find
that.
Yeah, I think our department has some funds, and that can help those students request. It's not the default section. We have experienced that students request for waiver of application fee, which I believe is $65. And our department has funds to cover that for those, to accommodate those requests.
Great. And then my other question that's more related to the science. So I'm a small molecule person. And when I see the synthesis that you're doing around this architecture, that makes sense. When I see the inspiration enzyme though, it's got 1,000 amino acids in it, and you just drop that when you go to using that as inspiration for these. But biology must have chosen that huge protein for a reason. And so in dropping the whole structure that holds this thing together in its biological context, there must be some compromise too. something.
Absolutely.
And I don't expect a full answer here, but I'm just
Okay,
curious. 'cause
I
it's
could,
short.
I could give my take and
Yeah.
then Don could elaborate. So yeah, you're right that nature does develop those, they were developed for a reason over billions of years. And it's also a fact that these enzymes, they could do stuff that we can't. We're not to the point where we can selectively oxidize methane to methanol so efficiently. We believe, of course, we know that that's done through the high valent metal center as part of the mechanism, but the issue of selectivity is likely to come from the secondary coordination sphere and further out, where the molecule is trapped in the active site and it can perform the chemistry and then be ejected. Here, when, as you alluded to, with these small molecules, we have no selectivity. So we're not to that point. And there has been groups where they try to synthesize some sort of secondary coordination sphere to trap the methanol or some intermediate to avoid it diffusing away. But I think that is a drawback to small molecule synthesis. But we believe there could be a way around it. There may be. And it's at this point, at least we're nailing down, we're investigating the reactivity purely on the metal to see if we could tune the metal. And then I think that can be a future direction to investigate.
And nowadays, one of the frontier research areas is artificial enzymes. So the idea is that you start from a native data, you extract the active site and feed the enzyme something. Even this could be something. Once we know better what this molecule can do outside the enzymatic scaffold, we can try to feed it back to one of those enzymes and try to alter or modify the routes for biocatalysis. I think that's one of the interdisciplinary research area. It's very hot. Frank Francis got a Nobel Prize because of that. Protein engineering and biology. So yeah, it's that's a field that requires expertise from entomology and biochemistry and the synthetic chemistry. That's something we want to contribute into as well.
Question, I don't know.
Dr. Lee?
Yeah.
You talked about how iron and copper, right, those are mostly used and you guys are switching to nickel and cobalt, but I didn't quite understand why. Is it cheaper? Is it easier to access versus copper?
I think we want to understand if there's a reason why nature skipped over or doesn't use cobalt and nickel so much. We want to see if there's something fundamental to the chemistry of high valent cobalt and nickel that makes it not as attractive for nature to utilize. So we know that cobalt and nickel can access these high valent states and perform similar chemistry, but we're not quite sure why. There's no real definitive answer why that nature hasn't developed that. There has to be a reason. Is it some toxicity concern or some reason that we're not aware of? Yeah.
So for example, you're gonna try and figure out the best version on the next slide or whatever, would you then use that same one with copper just to show a comparison then between the two?
We could try. Yeah.
That's something we're working on.
Copper.
That's why we
It's yeah, it's interesting because as you move right. Go ahead.
Collin and the other students work with. We have a big picture, many pieces. Trying to put them together like puzzle, but we got to take this one step by one step, one problem at a time. So yeah, that's a very good question. Well, we don't have an answer yet, but something we're trying to find the answer for. Why are cobalt and nickel so special, or so not so special, or so why does nature choose to skip those two elements?
It's also interesting you brought up copper because as you move right, these high valent oxidation states become harder and harder to access. So iron 4 is relatively easy of the transition metals. It's relatively easy to access. I mean, if you go left, I mean, you have manganese and chromium that can access +6 or 7. Cobalt gets harder to access +4. Nickel is hard to access +4, but it's possible. Copper is very difficult to access +4. Even +3 is difficult to handle. They get harder to handle and more reactive, and at a certain point, you get inevitably the complex starts reacting with itself. So yes, there's going to be some future work
Yeah,
on that.
there's not a single example of copper form complex. If we can make one of that, you will be satisfied.
Copper 3 is about the hottest it can get. Yeah. Heath.
How did you confirm that you synthesize what you think you synthesized?
As far as which part? The ligand?
Any of the intermediates?
So I typically use NMR for the synthesis. So I will check the NMR of the crude product and observe if it's there. And then I can use a chromatography to purify it and then use NMR for the purified species. And then as far as these, for that one, we know we synthesize that because we have a crystal structure obtained for it. And
Yeah, and there are many characterization of those states spectroscopies. Here shows you, crystal structure. And some UV spectroscopy. And there are many other spectroscopies like electromagnetic resonance, X-ray type absorption spectroscopy, Raman vibrational spectroscopy, FDIR. There are many things. We come up to this conclusion not based on just a single piece of evidence. So we typically when we get a new compound complex, try to characterize it as using as many approaches as possible. And when all the pieces come together, it's a single conclusion. We're happy. So.
Well, thank you very much. So you'll get some applicants from any field here.
okay. Well, it's a nice one.
Nice to meet you. Thanks for coming down. We'll have to stay in touch. And I saw Holocaust saying on that. I met him a few times. Now I see what the theory is.
Okay.
But yeah, nice to meet you. Really good to see you. Stay in touch.
It's
Let me
good
know
to
when
see
you
you.
get your first publication.
Awesome.
Is that pretty paramagnetic on the nucleus? Like, does it fire up? I've seen from the NMR question.
Schedule 3 is current.
Yeah, okay, so your NMR is just in one, so.
Well, we can do